Welcome to another short episode. Actually, I did not plan to make another video that fast. However, the other day, playing with this Lenovo T470s, I noticed that audio quality was not the very best and all the low frequencies were lacking a little bit. So when people tell you something does not sound as awesome, there must be a scientific reason for this, and what you would normally do is measure the frequency response of the various frequencies. Starting from this human ear, you would normally be able to hear between the range of 20 to 20,000 hertz, and ideally this curve should be entirely flat. But even higher end devices like professional Sony studio reference headphones do not have an entirely flat frequency response. Everything will have some frequency response curve. It will never be entirely flat. High-end microphones may be quite flat. Higher-end professional studio reference headphones may be quite flat. Loudspeakers are usually not that flat, and so on. So I personally would not buy some fashion equipment like Beats headphones and go with some more professional gear, because I also think usually they take more development resources to develop really working products. So the signal is produced in your device, and the signal produced should already be entirely flat. But unfortunately, the signal produced is also not entirely flat, and I can show you this a little bit. So to measure this, I went ahead and soldered 100 ohm resistors to the left and right channel to modern 4-pin TRS jack. So we will plug in this into the headphone jack for the measurement. And I connected this to the next best digital scope that I happen to have around. I will use an open source software SOX to generate some signals, and we will take a look how they look. So this is a Lenovo, and this is supposed to be a 20 kilohertz signal, and it actually looks quite okay. And we see an amplitude of about 280 millivolts, plus minus, give or take. So normally we would want to do this over the whole range of frequencies and make a pretty graph, but we will only look on some individual samples. So this is 10 kilohertz. It still looks quite okay. Similar amplitude. 1 kilohertz, still quite okay. 100 hertz. So 100 hertz, and with 100 hertz you see that the amplitude dropped quite a bit. So we had 280, and at 100 hertz we only have half of the amplitude left, meaning the output drivers do not have the power to drive a current for such a long time with the load of the headphone. So this is exactly what I was able to hear, that the low frequencies were lacking quite a bit. Can go down to 50 hertz, and even less is left of the signal. Ignoring for a bit that the signal looks a little bit noisy. That can also be the digital scope. Obviously it's not the very best for this task. To show you how bad this DAC, this digital analog converter and connected headphone amplifier really is, let's try a square wave instead of a sine wave. So this square signal at 1 kilohertz is obviously not very square. For office telephony and some occasional system sounds and music listening, this is okay, but it's obviously not the highest performing audiophile setup. So this is 500 hertz. You also see how much the signal is bouncing and overdriving, basically ringing and distorting. So it's not only that the bass is lacking, it's also that in general the frequency distortions are quite high. This is supposed to be a 100 hertz square wave, and we will later see how it actually really should look like. So again, this is obviously a business laptop, and you can actually listening music to this. It does not sound so bad. I think many people would probably not have noticed this. I could probably give this to 100 people on the street and they probably would think this is okay. So this is maybe also a little bit due to my audio and signal processing background that I actually realize this at all. Music does sound like music, it's just that the bass is missing, and in general it's not as crystal clear. So I also have a Microsoft Surface here. So this is 20 kilohertz. Surprisingly, decades ago with analog circuits, high frequencies were much more problematic. With these digital circuits, it appears to be that the high frequencies are much easier to achieve, and these portable devices have more challenges with output power, driving the outputs with a higher current for longer time in the low frequencies. So this looks quite okay. 20 kilohertz, 10 kilohertz, 1 kilohertz, 100 hertz. Like the Lenovo, the Microsoft Surface has a much lower amplitude at 100 hertz. Down to 50, and you see 50 hertz. There is not so much signal left. So if we would draw a graph of this, it would actually look similar to this example that I printed from the internet, where we certainly see some fluctuations on the higher frequencies and quite a significant drop at the low frequencies. Also the square waves. So 1 kilohertz square wave, actually I think it looks slightly better here on the Surface. 500 hertz, and again that does not look like such a nice square wave. And the 100 hertz square wave. We can also change the voltage square that we see this overdrive a little bit better. Here this is supposed to be square wave, and it should not be so difficult to get a pretty square wave. To also show you some nicer signals, I got the DAC high resolution portable headphone amplifier that we will hook up next. The DAC headphone amplifier is connected with a USB cable to the Lenovo laptop, but doesn't really matter where it's connected. And we're using this as a secondary ALSA device. So this is how 20 kilohertz looks like. Amplitude of 250 millivolt, 10 kilohertz, 1 kilohertz, 100 hertz, and 50 hertz. We see that the amplitude is much more stable. So this high-res headphone amplifier has a much more linear frequency response. The DAC headphone amplifier has a Texas Instruments Brown DAC and certainly a more carefully designed output driver stage, while both laptops only have an entry-level Realtek codec. So let's take a look on the square waves. So here we see how a square wave actually should look like. Namely, it should be square and not a randomly drawn curve. This ringing that we see is quite normal and actually quite good for this $300 portable device. So 500 hertz and 100 hertz. I think the difference in the quality of business laptops and more audiophile related products becomes most apparent when we take a look on the signal form of the square waves. So you can still use those machines to listen to music, and most people may not even notice the difference. For me, what I actually realized quite quickly was the missing low bass frequencies. In earlier times in the 90s or so, when audio equipment was tested, they usually measured the frequency response. And this is also what I find lacking in so many reviews nowadays. In my opinion, they often only list the feature set and do not really test the quality of the individual components. That is not to say that I will always test each and every feature, but I will try to give a different developer, IT professional perspective to the products we are taking a look on. So thank you very much for watching. I hope you found this useful, and don't forget to subscribe for the next videos to come.